So let us move towards the classical statistics, okay, in which we'll study Maxwell-Boltzmann statistics, or it is called as Maxwell-Boltzmann statistical distribution function. The classical or Maxwell-Boltzmann statistics is mainly applicable to system of distinguishable particles. For example, if you take the system of gas, okay, the gas system contained in a container, then those particles are distinguishable. They are not identical, not same to same. They are different from one another. So that is the main assumption in Maxwell-Boltzmann statistics. So even though the system is consisting of mixture of particles, okay, different particles, then this Maxwell-Boltzmann distribution function is applicable. It does not consider the Pauli's exclusion principle. Remember, classical statistics does not consider the Pauli's exclusion principle. Hence, any number of particles can be accommodated in a energy state. They can occupy any number of energy states. So if you take the energy state, in the energy state, you can put any number of particles. Okay, you can put 100 particle, 200 particle, it doesn't matter. Therefore, in Maxwell-Boltzmann statistics, there is no restriction on the number of particles to occupy an energy state. You can put any number of particles in the given energy state, or you can find large number of particles having the same energy. So in other words, you can say that you can find a large number of particles of same energy. Okay, so it is applicable to distinguishable particle. Distinguishable means they are different from one another. They are not identical. From one particle to another particle, you can observe the difference between them. So it can be considered as mixture of different kinds of particle. That is the meaning of distinguishable particle. Then consider the system constituted by n number of distinguishable particle. Let n1, n2, n3, so on up to ni be the number of particles with energies E1, E2, E3, so on up to Ei. Okay, so in the energy state E1, there are n1 number of particles. In energy state E2, n2 particles are there. In E3, n3 particles are there, like that. There are I number of energy states, and in each state you can find a different number of particles. There is no condition on number of particles in the energy state. Then what are the total number of particles present in the system? That is given by capital N is equal to N1 plus N2 plus N3, so on up to Ni, and it is considered as summation of Ni. Okay, so total number of particles N is equal to summation of Ni, where I runs from 1 to N. And what is the total energy? We know that energy of first state is E1, and there are N1 number of particles. Therefore, total energy of first energy state is E1 into N1. So E1 represent energy of one particle into number of particle. Similarly, you have to add it to energy of second state, energy of third state. So that will give you total energy E is equal to E1 N1 plus E2 N2 plus E3 N3, so on up to Ei Ni, which is equal to summation of Ei Ni. Okay, so total energy is given by summation of Ei into Ni. Total number of particle is given by summation of Ni. Okay, and already we have observed the conservation laws. According to conservation law, the total number of particles in the system and the total energy of the system are conserved. They are going to be constants, okay, under the equilibrium condition. So if total number of particle is constant, then definitely derivative of n must be equal to 0. Okay, so change in n should be 0. There is no change in n. So n is going to be constant, therefore it cannot change. That means dn should be equal to 0. If you take the derivative, it will be equal to dn1 plus dn2 plus dn3, so on up to dnn should be equal to 0. Okay, otherwise you can write in terms of energy, the change in energy is also going to be 0. Okay, remember energy of first state is constant, where there may be change in dn. So E1 dN1 plus E2 dN2 plus E3 dN3 so on up to En dNn should be equal to 0. Okay, and remember here dN1, dN2, dN3, they may be non-zero quantities, but you add them, that will lead to the value 0. That means there may be internal arrangements, internal changes inside the system, but entire system will contain the constant number of particles. Okay, that is the meaning. And if you express this in terms of summation form, this conservation of number of particles is given by summation of dni equal to 0, where summation runs from I equal to 1 to n, and energy conservation is given by summation over I equal to 1 to n of ei dni should be equal to 0. Okay, so these are conservation laws. Already we have studied in the previous class, and using these conservation laws we can derive the expression for the Maxwell-Boltzmann distribution function. We'll see. Now, according to the Maxwell-Boltzmann distribution function, how many number of ways you can put the system of particles in different microstate you have to consider. So we know that in Maxwell-Boltzmann statistics, you can put any number of particles in the given energy state. Okay, and particles are distinguishable from one particle to another particle. You can find the difference between them. Now let us take omega be the total number of ways in which n particles are distributed. Okay, omega is the total number of ways in which capital N number of particles are distributed in small n different energy states. Okay, the number of ways in which the group of particles, let us take n1, n2, n3, so on up to ni, are chosen from total n number of particles is given by omega 1 is equal to n factorial by n1 factorial into n2 factorial so on up to nn factorial, and that is represented as n factorial by product of ni factorial. So this is a product of n1 factorial, n2 factorial, so on up to nn factorial. So product of number of terms is represented by this pi symbol. Summation sigma symbol represent sum of number of terms. This pi symbol represents the product of number of terms. Note the difference here. This symbol is representing product of ni factorials, n1 factorial into n2 factorial into n3 factorial, like that. So just I will illustrate this. This is the expression which gives you different number of ways you can put the system in different microstates. So this represents the different possible ways of arranging n number of distinguishable particles. Just I will illustrate that. This relation is according to the permutation. Just to illustrate that, let us take a system of 3 particles A, B, C and 2 cells. Okay, so 3 particles are there in a system and 2 cells are there to accommodate them. And you know that any number of particles can be put in a given state. So first possibility, first cell contains all 3 particles, second cell is empty. So n1 is 3, n2 is 0. So according to the formula, what is the number of different possibilities? Omega 1 equal to n factorial by n1 factorial plus into n2 factorial, like that. Okay. So if you do that, n factorial will be 3 factorial, n1 factorial is 3 factorial, n2 is a 0, number of particles in the second cell is 0, 0 factorial. So 0 factorial is basically 1. So 3 factorial by 3 factorial gets cancelled. You will get only one number of way. Only one way is possible, A, B, C, like that. Let us take second combination, 2 particles in first cell, 1 particle in the second cell. You can find 3 different possibilities. So number of ways should be equal to 3. Let us check the formula. So formula says omega 1 equal to n factorial by n1 factorial into n2 factorial, so on up to nn factorial. Remember, n1 is 2, n2 is 1. Therefore, it will be 3 factorial by 2 factorial into 1 factorial. So that will be 6 divided by 2. That will give you 3. So 3 different ways are there. ABC, BCA, ACB, like that. Similarly, if you take one particle in first cell, two particles in the second cell, definitely again you will get three different ways according to the formula, and it can be illustrated like this. Last possibility, no particles in first cell, three particles in the second cell. Only one possible way is there. If you take the sum of all the possibilities, it will give you 8. 1 plus 3, 4 plus 3, 7 plus 1, 8. Therefore, the total number of microstates that is given by the number of states to the power number of particles, Gi to the power Ni, where Gi represents number of states. 2 states are there. Number of particles are 3, 2 to the power 3. So there will be 8 different ways. Individually, you can find the number of ways using this formula. In order to find a total number of ways, you take Gi to the power Ni. We have to use this to find the thermodynamic probability. Let us move further. So let us take the same system consisting of Ni particles, and they have to be arranged in Gi number of microstates with equal probability. Then the number of ways in which Ni particles could be distributed in Gi microstates is given by Gi to the power Ni. Just I have illustrated. 3 particles, 2 states. So total number of ways will be 2 to the power 3. Here Gi number of states, Ni number of particles. Total number of possible states will be Gi to the power Ni. So therefore, the total probability that will be equal to, so considering all n macrostate, this is corresponding to 1 macrostate. The total number of arrangements will be omega 2 will be G1 to the power N1, G2 to the power N2, G3 to the power N3, etc. Where G1 is number of microstate in first state, G2 is number of microstate in first macrostate, like that. N1 is number of particles in first state, like that. So that is how we can find. Therefore, omega 2 will be product of Gi to the power Ni. Product of Gi to the power Ni. So you have to take G1 to the power N1, G2 to the power N2, like that. It is a product. So what will be the total thermodynamic probability omega? That will be equal to omega 1 into omega 2. Okay. So therefore, the total number of ways in which n particles could be distributed in n different state, that is given by omega is equal to omega 1 into omega 2. That is n factorial by Ni factorial, product of Ni factorial into product of Gi to the power Ni. Okay. So just to recall, omega 1 is given by this formula, n factorial by product of Ni factorial. Same thing is used here. Okay. N factorial by Ni factorial, which is kept in product form. Okay. Product of Ni factorial, that is N1 factorial, like that. So this gives you the all possible ways of a distribution of particle in accordance with Maxwell-Boltzmann distribution. And I have shared the notes. In that I have given you the appendix. Appendix okay, appendix 1. In there I have given you the different possible ways to put the system of particles according to different statistical distribution functions. Okay. So then using this, you can find out the distribution function, expression for distribution function. Let us see further. We have got total thermodynamic probability omega, which is equal to omega 1 into omega 2, which is given by n factorial product of Gi to the power Ni divided by Ni factorial. Okay. Taking natural logarithm on both sides. Take natural logarithm on the both side. The equation becomes, and apply Stirling approximation. The equation becomes ln of omega, which is equal to ln of n factorial plus this product becomes summation. If you take the ln of products, that will give you ln of individual sums. Okay. So this will give you omega ln of Gi to the power Ni minus summation of ln of Ni factorial. Why minus sign appears? Because Ni factorial is in the denominator. Okay, 1 second. So here, this is n factorial. If you take ln, that will give you ln of n factorial. The product means it becomes sum. Okay, because the ln of products, that is equal to sum of the terms. So it will become summation of ln of gi to the power ni minus summation ln of n factorial. I hope you have got this particular step properly, because this is a ln of this product. So ln of this product will be ln of sum of individual terms. So ln of n factorial plus ln of gi to the power ni, product becomes sum if you take the logarithm, because you know that ln of m into n is nothing but ln m plus ln n. So that formula I have used. So negative sign is because of the fact that it is in the denominator. So ln of m by n is nothing but ln of m minus ln of n. So that formula I have used. Next. You apply Stirling approximation. If you apply the Stirling approximation, you will get ln of n factorial is equal to n ln n minus n. We know that ln of n factorial equal to n ln n minus n. So use that formula plus summation ni ln gi. Okay, so it is represented as ln of gi to the power ni is represented as ni into ln of gi, because you know that ln of m to the power n is nothing but n into ln m. Okay, that formula I have used. Minus, apply the Stirling approximation again, it will be summation of ni ln ni plus summation of ni. This minus into minus becomes plus, plus summation of ni you will get. So what is this summation of ni? Summation of ni is nothing but total number of particles, capital N. Okay, so summation of ni is capital N. You keep other terms as it is. This capital N plus n minus n gets cancelled, and finally you will get n ln n plus summation of ni ln gi minus summation ni ln ni you will get. Okay, that is the formula you are going to get. And here we have used the identity summation of ni equal to capital N, which is representing total number of particles. So capital N gets cancelled. This is the formula for ln omega. Now you use the Boltzmann's theorem. So for most probable distribution or for the equilibrium distribution, the entropy of the system S should be equal to k ln omega. So entropy S will be equal to k ln omega of the system should be maximum. So for equilibrium distribution, what will happen? The most probable distribution is entropy of the system should be maximum. Now, according to Boltzmann's theorem, the entropy is related to ln omega by S equal to k ln omega. Okay, that is the formula. S equal to k ln omega. So entropy is maximum means derivative of the entropy must be equal to 0. If S is maximum, derivative of the entropy must be equal to 0. Okay, so therefore dou S, which is represented as k into dou ln omega.
Recording in progress.
So dou S will be equal to k into dou ln omega. That should be equal to 0, because if S is maximum, this dou of ln omega should be equal to 0. So take the derivative of ln omega, that should be equal to 0 for the most probable distribution. So therefore, you will get dou of ln omega, which is nothing but dou of ln omega we have obtained in the previous slide, that is n ln n plus summation of ni ln gi minus the summation of ni ln ni, which is equal to 0. So you have to differentiate this with respect to ni. Okay, because ni is the variable. Total number of particles, capital N, is constant. Total number of state gi is constant, where ni is the variable, which is going to change. Okay, so therefore the derivative with respect to ni you have to do. If you do that, partial derivative, if you do that, first term is constant, therefore derivative of the first term is 0. Okay, so by using the Ego equation, you can differentiate this with respect to ni. Same term. If you differentiate the first term with respect to ni, which is constant, which is 0, derivative of constant is 0. Derivative of the second term is summation of ln gi into dou ni. Okay. And the last term minus ni into ln ni. So if you do that, you will get a ln of ni into derivative of ni. So that is dou ni. So equal to this equation becomes equal to summation of ln of gi minus ln of ni into dou ni, which is equal to 0, because dou of ln omega should be equal to 0. Dou of ln omega should be equal to 0. Because of that, you can get this particular summation should be equal to 0, where gi and n are constants because they are conserved. Number of states and number of particles are conserved. Okay. So if this equation is true, then each and every term should be equal to 0. Now you will use the concept of conservation law. We know that summation of dni equal to 0 and summation of ei dni equal to 0. Now we will multiply this equation by non-zero numbers, say minus alpha and minus beta, and this identity will not change. And this method is called as Lagrange's method of undetermined multiplier, where alpha and beta are unknowns. Multiply them, okay, and then add these two equations to the ln omega equation. So multiply minus alpha to this particular first term, minus beta to the second term. So you'll get minus alpha into summation of dni equal to 0, minus beta into summation ei dni equal to 0. Now add these two equations to the previous equation obtained. Okay, adding these two to the above equation, you will get summation ln of gi minus ln of ni into dou ni minus alpha into summation of dni minus beta into summation of ei dni. Take dni as a common factor and you will left with summation ln gi minus ln of ni minus alpha minus beta into ei into dou ni equal to 0. So dou ni is taken as a common factor throughout the equation. Then you will get this particular equation, and here this alpha and beta are undetermined multipliers. Now we have to find alpha and beta so that each and every term in the summation should be 0, because alpha and beta are constant, they are non-zero. Therefore, each and every term in the summation should be 0. Okay. The unknown constants alpha and beta are to be determined such that the term in the bracket vanishes for all values of I. Therefore, ln of gi minus ln of ni minus alpha minus beta into ei should be equal to 0. Next, rearrange them. Consider ln of ni, that will be equal to ln of gi minus alpha minus beta into ei. So take the anti-log on both sides. Take the anti-log on both sides, you will get ni on the right hand side. If you take the anti-log of log of gi, that will give you gi. Anti-log of this minus alpha minus beta into ei will be exponential to the power minus alpha minus beta into ei. Taking natural anti-logarithm, you will get this particular expression for ni. And here ni by gi is known as the distribution function. Okay. Otherwise, ni, the total number of particles in the system, is always represented as a product of number of states into distribution function. That is the common platform for finding the number of particles in the system distributed in accordance with certain distribution function. So therefore, ni is always represented as gi into f of ei. Here, f of ei is called as distribution function. And this equation is derived by considering the conditions provided in the Maxwell-Boltzmann distribution statistics. Therefore, this particular distribution function f of ei should be called as Maxwell-Boltzmann distribution function. So the function represents the ratio of number of particles to the number of states in which they are distributed. Basically, this distribution function is defined as number of particles, ratio of number of particles to the total number of states. Okay, that ratio is called as distribution function. Therefore, according to this equation, if you compare these two equations, you will get the function f of ei is equal to ni by gi, which is represented as e to the power minus alpha minus beta into ei. And this f of ei is called as Maxwell-Boltzmann distribution function, which is applicable to system of spinless distinguishable particles. Okay. Finally, it can be proved that beta equal to 1 by kt. We can prove this Lagrange's undetermined multiplier beta is equal to 1 by kt, where k is Boltzmann constant, T is absolute temperature. Substitute beta equal to 1 by kt, you will get f of E, that is FMB. I will take Maxwell-Boltzmann distribution function, that is equal to e to the power minus alpha minus e by kt. Okay, beta e is replaced by e by kt because beta equal to 1 by kt. It is with negative power, that is represented as 1 by e to the power alpha plus e by kt. Okay, e to the power minus alpha minus e by kt is represented as 1 by e to the power alpha plus e by kt. So this is called as Maxwell-Boltzmann distribution function. Using this, you can find a total number of particles in the given state, and that is given by a simple formula. N of E is always equal to the number of state G of E into distribution function F of E. That is the simple formula. If you do that, that will give you G of E divided by e to the power alpha plus e by kt. So using this Maxwell-Boltzmann distribution function, you can find out the number of particles in the given state. So these two equations represents the condition according to which the number of spinless distinguishable particles are distributed in the available states. This is called as classical statistics or Maxwell-Boltzmann statistics. Okay, so these two equations are very important in study of the classical system. Okay, and finally, the Maxwell-Boltzmann statistics is applicable to dilute gases system and to free electrons in the conduction band of the semiconductors at finite temperature. Where this Maxwell-Boltzmann statistics is applicable, it is applicable to the dilute gaseous system, and it is applicable to free electrons in the conduction band, where the particles are assumed to be distinguishable. Okay. So therefore, finally, two equations you have to remember. The Maxwell-Boltzmann distribution function FMB of E, which is equal to 1 by e to the power alpha plus e by kt. That equation you have to remember. And the average number of particles distributed in the GI number of state, it is given by N of E is equal to G of E into F of MB of E. That is G of E divided by e to the power alpha plus e by kt. Okay. So this is how you can derive the expression for the Maxwell-Boltzmann statistics or classical statistics.